So here we're doing a weak base strong acid titration. You can see we have the base in the flask and our titrant is the HCl, our strong acid. You have your concentrations of both and you know how much base you started with in the flask. So you can answer this question, what is the initial pH in the flask? Because we're just taking the initial pH of a weak base and we know it's a concentration. So it's a very straightforward ice chart. You're given the Kb of the base. Another pretty straightforward question is using this neutralization reaction. We have a single arrow. What volume, in this case we're asking, of the HCl is needed to reach the equivalence point? Sometimes you'll be asked to find a molarity, but since you have both molarities, the unknown piece here is what's the volume that we would need so that we have the same amount of moles of our base as our acid. We did straight up stoic here. You need the mole ratio from your balanced equation. Do remember that a strong acid will essentially just be H3O plus in solution, and then that'll get your H2O on the product side. And then we have our answer here. So this is straight up stoic. I mean, this was like a, first year stoic problem. Now we're gonna get into a more challenging question. We're gonna look at the pH at any point in our titration. So not at the start and not at the equivalence point, but when a certain amount of, in this case, our acid is added 5 milliliters, okay? So now we actually know how many milliliters here. We can figure out moles of stuff and figure out like what our limiting and our excess reactants are. So that's this slide. This is like moles at the start, change in moles, moles remaining. So to get your moles, you multiply your volume and your molarity. We did that in both cases here. We assume we start with 0 for our products. Then, since this is our smaller value of a 1-to-1 ratio, this is going to be our limiting reactant. This is our excess reactant. We know how many moles of our excess reactant remains. We know how many moles of these things we formed. Water is not important, but your conjugate acid actually is important because when you're calculating your pH, you're going to need this concentration. It's moles right now, but you'll need a concentration. So all the work is still here, but now we're looking at step 2, which is finding the molarity of the excess reactant, the amount that's left over at least. So we know this many moles is left over of our base, and then this is our total volume from our 25 mils plus the 5 that were added, and we can calculate our molarity of our NH3. Just be careful, that's not equal to hydroxide ion concentration because we have a weak base. Again, all of this is repeated, and then now we can find the pH of our NH3 solution. So we put the value we just found for molarity in here, but be careful, we do have some conjugate acid. So we calculate the molarity of that we're starting with. We're assuming we don't have any OH minus at the start. We set up our ice chart. And we end up solving for X. X is our hydroxide ion concentration. We can make the assumptions here, no worries. If you take the negative log with that, you're going to get your POH and then subtract that value from 14 to get your pH. And it does make sense. Your pH value is still basic, but it is less basic than it was at the start because we've added some acid. So the last question is, what is the pH at the equivalence point? And you're going to use your stoichiometry that you already did to find how many milliliters of hydrochloric acid need to be added to reach the equivalence point. At the equivalence point, the moles of your base and your acid are going to be the same. And since it's all 1-to-1 ratio, your moles of your conjugate acid are also going to be the same. So we need the molarity of the conjugate acid. So the moles divided by the total volume in the flask at the equivalence point. We need that because this will hydrolyze, right? It will react with water and it will produce some H3O plus. So that's why you don't have a pH 7 at the equivalence point. And then once you have this information, you can set up your ice chart. Now, please note, we're not using the NH3 here anymore. We're using the NH4 plus, and this is the acid reaction. So while you have a Kb for NH3, you need to get the Ka for NH4 plus. So just Kw over Kb to get that. And then you can solve, your pH ends up being 5.16 at the equivalence point, which is what we would expect from a strong acid weak base titration. The pH is going to be lower than 7 at the equivalence point.